We're going to work through a linear regression problem on MLPro. So in this open-ended problem, we're given a housing data set. In particular, we're given a list of houses, and for each house, we're given information such as the per capita crime rate by town for that house, and proportion of non-retail business acres per town of the town that house is in, and a bunch of other information. We could see the data here. It's a NumPy array where each row of the NumPy array is a different house, and each column represents one of these values, attributes of a house. And we're trying to predict the cost of the house in the 1970s in thousands of dollars. So that is our Y-train variable. So this is a regression problem because we're trying to predict the price of the house. And so if we run the solution that comes by default in this problem, we hit run, we get a mean squared error of 151. This is not a good value. Mean squared error represents error. It's how different your prediction was from what the value should have been. So this is a pretty high error given, even squared error, given that, these are the values of the houses we expect. So like the square root of 151 is about 12. So we tend to be off by about 12 point something. That's a large amount. Imagine this is supposed to be 15, but instead it predicted 27. That's a ways off. So how can we reduce this mean squared error? There's many techniques we could add to a basic linear regression model. We have many options, and there's kind of two routes we can go. One route is to notice that our data set is very small. This is the entire data set. Just to quantify it, let's actually print out the value of how many rows there are. So if we print xtrain.shape, we see that there's only 41 rows in our training data. That's very, very small data. So that means the implication for that is that the model can easily overfit to the training set. How can we prevent overfitting? There's many methods, but a very popular one is called regularization. So scikit-learn comes with a regularization functionality. It includes ridge regularization. We'll talk about what that means in a bit. So if we just swap out linear regression with ridge regularization, we notice that, wow, our mean squared error already goes down to 87, much better. If we swap it out again, this time with Lasso regularization, which is closely related to ridge regularization, wow, the mean squared error goes all the way down to 16. And we can further mess around with the regularization strength, or the alpha variable, and potentially lower our mean squared error further. Wow, we got it down to 5. So, okay, so why does regularization improve things so much? Well, let's look at the equation for regularization. So let's see. Let's use Wikipedia. Wikipedia has get straight to the point sometimes. Maybe not in this case, but oftentimes it does. Okay, no Wikipedia. Let's use the scikit-learn documentation. They do great. They get very much to the point. Okay, great. Here we go. So the optimization objective for Lasso is this equation. So let's break this apart. Let's first observe that this first part is basically the same optimization objective that is used for linear regression without any regularization, because essentially we are looking at the difference between what the true value is, that's just the y value for each data point, and what the model predicts for each data point. In other words, what's the weight of the model times the input of the model in linear regression. So We take the difference, take the square, that is our mean square error, and well, that's the objective we're trying to optimize for. So we want to minimize this difference. We want to minimize the difference between what the model should predict and what it actually predicts. Ideally, there wouldn't be any difference, so we get a 0. Anyways, that's regular linear regression. However, with the regularization, we add this extra term here, plus alpha times the weights of the model. So why do we do that? Well, if we keep in mind that the goal of linear regression is to minimize this difference, we want this value to be as small as possible. However, if we add to that value that we're trying to minimize, we add some constant alpha times the weights of the model. That means that if your model has more weights, if there's more m's in the mx plus b's, you have m1 x1 plus m2 x2 plus dot dot dot. If you have more m's set to non-zero values, then this thing you're trying to minimize is going to be higher, but you're trying to minimize it. You're trying to make it go lower. And therefore, by adding this extra term and saying you're trying to minimize this entire equation, what you're doing is you're essentially saying that if you add more weights to the model, you're not going to get this to be the lowest that it can be. So the only way to get this whole equation to be the lowest possible value that it can be is to have a lot of the weights of your model be set to 0. What that means is you're setting a lot of the m's in the mx plus b to 0, which means a lot of the input values, in other words, a lot of these columns are going to be ignored. And that's good to prevent overfitting. You're basically saying, how can I learn with this data using the least amount of this data possible? And the reason we really want to do that for this data set is, again, it only has 43 rows. It's a very tiny data set, which means without regularization, it's especially prone to overfit to this data, these data specifically, and not to the held out test set. And that is why Lasso regularization does particularly well. Another approach you could have taken would have been to use a non-linear regression method. So linear regression is highly limited because it's limited to finding lines or the equivalent of a line in higher dimensional space, so a plane, hyperplane, but it's these very linear shapes in whatever dimension you're operating in. And so you often data does not follow those trends. Like it could be a curve, or it could be a squiggly line, or it could be a circle. So the only way you could possibly learn some of those patterns is to use nonlinear regression methods. So for example, polynomial regression, or you can use a decision tree for regression, or a bunch of other techniques. So that could have been another approach you took. So I hope this was helpful, and stay tuned for more open-ended questions on MLPro.